Traditionally, suspensions in motocross racing have simply consisted of coil springs and oil dampers. This system has worked well over the years, but coil springs are very heavy, which slow down the bike's rebound speed, and they do not allow riders to adjust the response of their bike for different track conditions. For these reasons, compressed air forks have recently become popular, but they have not been widely accepted because they are too rigid on high impact and aren't very durable. Last year, Showa released a new design that consists of 3 air chambers in one side of the fork and an oil damper in the other side of the fork. This makes the suspension system highly adjustable, durable, and responsive at different levels of impact. One of the chambers is inside of an outer chamber to maintain suspensions even if a seal blows and the other chamber sits underneath and counteracts the downward force of the other 2 chambers, preventing the fork from topping out. The low weight of this system also increases the rebound speed, allowing the rider to quickly recover from impact. The fork also allows not only adjustment of the damping effects, but also of the pressure in all 3 air chambers, making the response and ride of the fork customizable to any rider's needs.
The suspension travel describes how much the wheel of the motorcycle is able to move up and down. The terrain that the motorcycle will be driven on is the biggest factor to consider when designing the suspension travel. The first objective is to have as smooth of a ride as possible. The second objective is to have the tires maintain contact with the terrain's surface. The dimensions of the motorcycle are one constraint to take into account. The shocks have to be short enough that a person can get onto the motorcycle. The suspension travel is constrained by the chain of the motorcycle. The chain will snap if enough tension is placed on it, and it could slip off if it gets too loose as the wheel is moving up and down. Because of this, a tensioner is used on the rear wheel of the motorcycle to account for the suspension travel. Since some motorcycles are driven on rough and smooth terrain, a rising rate suspension is used. With this suspension, the spring changes tension as it compresses. This variable stiffness of the spring in the rear shock allows motorcycles to handle rough terrain and smooth terrain.
Rebound damping refers to the speed at which the spring and fork in the suspension return to their original position. For example, a highly damped fork will return to its original position very slowly. It is important to have a balanced level of rebound damping. If rebound damping is too low or too high, there will be a loss of traction. If it's too high, the spring will fail to return to its proper position fast enough. If it's too low, the chassis may actually be thrown off the ground because the front fork basically becomes a pogo stick. In both cases, contact with the ground is interrupted after hitting a bump or a pothole. Having too much rebound damping is uncomfortable for the driver, and having not enough may be comfortable at low speeds, but at high speeds the driver will feel out of control. In general, the effects of compression damping are very similar to rebound damping. On most bikes, the compression and rebound damping may be adjusted manually in order to find the happy medium.
Anti-dive technologies were first engineered between the 1960s and 1980s. There were 2 main types, the Honda Track system and the Yamaha AVDS system. The intended purpose of an anti-dive suspension is to keep the front suspension from depressing a long distance, otherwise known as diving during fast deceleration. This diving of the front end can cause the rider to rotate over the handlebars, or at the very least the back wheel will lift off the ground, resulting in a loss of control or traction for an inexperienced driver. The track system utilized a brake caliper attached to a pivoting bar behind the center of the wheel. When the brakes were applied, the caliper rotated forward and depressed a valve that decreased the area of flow in the shocks. This increased the stiffness. The AVDS system used a third hydraulic cylinder that used the pressure built up in the brake line to compress a valve in the hydraulic cylinder that restricted the hydraulic fluid movement, stiffening the suspension.
Upside-down forks, or better known as inverted forks, were incorporated by racing teams in the later part of the 1980s. To understand the benefits of inverted forks, a comparison with conventional forks is necessary. There's almost no difference between conventional orientated forks and inverted forks in operation. The big difference between the two is their strength. Inverted forks are much more rigid because they are held by a larger diameter part of the fork called the slider. Conventional forks are mounted by the stanchion. By comparing the inverted and conventional forks, you will also notice the slider is much longer on the inverted forks. The slider is the more rigid portion and makes up a higher percentage of the overall length of the inverted fork. This reduces flex and improves handling and feel. Conventional forks have the advantage of requiring less maintenance and having a longer lifespan. Inverted forks tend to get damaged easier by road debris and are more difficult to repair due to their inverted structure. The final advantage for inverted forks is their weight. The steel stanchion is the heaviest part of the fork assembly. Inverted forks have shorter and thinner walled stanchions. This directly relates to lessening of the steering inertia, which creates a more responsive feel.
I will briefly talk about cartridge emulators in damping rod forks. Traditional damping rod forks use a fork piston that has holes called orifices that regulate the compression and rebound damping. These holes are fixed in size, and as such, the fork has fixed damping characteristics. The solution is to install a cartridge emulator. These take the job of compression damping away from the fork piston by use of a sprung valve, as well as by increasing the size of the orifice holes. This valve is shown on the bottom right. Rebound is unaffected and still unadjustable. However, the ride is greatly improved. A graph of the damping force versus the fork velocity is seen on the bottom left. The top curve is for a fork with an emulator and shows that the ride is firm and comfortable throughout the range of velocities, while the bottom curve is for a fork without an emulator and shows that the ride goes from very mushy to the pain zone